You see this all the time. A team builds a vector search system, tests it on a small clean dataset, gets great results, and thinks it's ready for production. But once the app is exposed to real messy data at scale, weird things start happening. The results are semantically similar to the query, but now they're sometimes irrelevant or out of context. And in this situation, most teams aren't sure what the problem is or how to diagnose it. In this video, you'll learn why this happens and what a production-ready retrieval pipeline looks like beyond just vector search. And if you're just learning about vector search, you'll want to check out our What is a Vector Database video and other episodes in this series to quickly get you across the basics. Let's get into it, starting with vector similarity versus retrieval quality. Vector search returns the mathematically closest vectors to a query, but that's it. It has no idea whether those results are actually relevant or correct for the user. Here's a concrete example. Let's say a user asks, "What's your refund policy?" The search returns a chunk scoring 0.94, which looks great, except it's the refund policy for the wrong country. The score told you it was semantically close, but it was contextually incorrect. That's the gap between similarity and retrieval quality. Retrieval quality is asking a different set of questions, such as how many results were irrelevant? Were the most relevant results ranked first? And most importantly, could the question actually be answered from the results? A high similarity score can't guarantee any of that, which is why most teams implement a retrieval pipeline where vector search is just one of several steps. But often, what seems like a search or retrieval problem is actually a data quality problem, which is why data preparation should be your first priority. Your retrieval pipeline is only as good as the data that it's searching. It can't surface results that weren't captured, it can't filter on metadata that wasn't added, and it can't return coherent answers from chunks that were split mid-sentence. And even the best vector database with the most sophisticated retrieval pipeline won't save you if the data you're searching is noisy and poorly structured. Most retrieval failures are baked in before a single embedding is generated, but there's 3 steps that can prevent that. The first is cleaning, filtering out irrelevant documents, removing duplicate content, and stripping noise like PDF headers and footers. The second is metadata enrichment, attaching structured attributes like region or category. This is what makes filtering possible later, so you're only returning relevant results. The third, and most commonly undervalued, is the chunking strategy. How data is divided into separate embeddings. The goal is that each chunk is a meaningful semantic unit on its own. For example, if you're indexing code, a chunk shouldn't end mid-function. If you're indexing a knowledge base, a short FAQ might be one chunk, while a long article gets split by section headings. There are 3 main chunking strategies. Fixed length, which splits at a character or token boundary with no semantic consideration. Sentence-based, which prevents incomplete content but minimal semantic consideration. And structural, which uses headings, sections, or other logical divisions. Chunking is a deep topic, and we'll be dedicating an episode to it later in the series. With clean data and coherent chunks, you've got the basics right. Now let's look at what the retrieval pipeline actually looks like. The most common steps you'll see in a production retrieval pipeline are query rewriting, an index, metadata filtering, hybrid search, and re-ranking. Together, they address the failure modes that pure vector search can't handle on its own. User queries are often missing key details and context that negatively affect retrieval quality. Query rewriting solves this by transforming the raw query into a form that will return more relevant results. This is typically done in 2 ways. The first is query expansion, expanding upon the initial query, for example refund, to make it more fully formed and increase similarity with relevant content. The second is context injection, which enriches the query with information the user didn't think to include or couldn't, such as country, organization, or membership tier. A flat index contains every vector in the database, but once searching all vectors exceeds your latency or infrastructure constraints, an approximate nearest neighbor or AN index is used, trading a controlled drop in recall for speed and memory efficiency. The two most common AN indexes are HNSW and IVF. HNSW navigates a graph of vectors, giving higher recall at lower latency, but at the cost of more memory and more complex index maintenance compared to IVF. IVF searches within pre-clustered buckets, making it more memory efficient at high throughput, but with typically lower recall than HNSW. The right choice and optimal configuration depends on a range of factors, and we'll be diving deeper into AN indexes in the next episode of the series. Metadata filtering is the vector search equivalent of an SQL where clause. It lets you scope results to only the data that's relevant for a given user or context by attaching structured attributes to chunks at index time. But unlike SQL, filtering can occur pre or post vector search. Pre-filtering applies the metadata constraints before similarity search runs, which reduces the number of vectors being searched. Post-filtering runs similarity search across the full index first, then excludes invalid results. If using a flat index, pre- and post-filtering return the same results. But when an AN index is used, pre-filtering can result in a poorly connected graph where valid results are no longer reachable. While vector search excels at retrieving semantically similar content, it can miss results that are an exact keyword match but aren't semantically close to the query. That's where hybrid search comes in, merging vector and keyword results into a unified list using a ranking algorithm. Reciprocal rank fusion, or RRF, is the most popular choice, as it ranks results based on their position and occurrence in one or both result sets, which is simple to understand and implement. While results from a vector or hybrid search may be returned in similarity order, that doesn't mean it's the optimal order. Re-ranking addresses this by re-evaluating the query against each result using a cross-encoder model that scores the query and each result together as a pair. That makes it significantly more accurate at ordering results by relevance. Re-ranking often has the biggest impact in a retrieval pipeline, but it comes at a cost in both compute and latency. There's one more thing worth understanding before we wrap up, which is pipeline retrieval latency for on-prem environments. Every step in a pipeline eats into your latency budget. In cloud environments, scaling up infrastructure is usually enough to keep that under control. But for on-prem or edge deployments where compute is fixed and constrained, your latency budget is tight from the start. As vector search latency tends to be the most variable point in the pipeline, speed and efficiency are often the most important considerations when choosing an on-prem vector search solution. That's everything you need to go beyond basic vector search and start building production-capable retrieval pipelines. If you want to go deeper or share what you're building, join the Actian community on Discord. The link is in the description. Thanks for watching, and hope to see you in the next video.